Welcome to the Meet the Experts debate with Offshore Engineer, brought to you from the Offshore Europe 2013 exhibition and conference here in Aberdeen, Europe's oil and gas capital. These debates are brought to you with GL Noble Denton, and this is one of two debates that we're bringing you this week. Now, GL Noble Denton is part of the GL Group. It's an independent technical advisor to the oil and gas industry, who helps some of the industry's best-known companies reduce risk, meet stringent regulations and increase efficiency by applying global best practice in safety, integrity and performance across the life cycle of on and offshore assets and operations. GL Noble Denton have a presence in more than 80 countries and a team of nearly 4,000 engineers and scientists with a strong presence here in Aberdeen. Now, we're here for a discussion and question and answer session on floating production and specifically advanced inspection and maintenance strategies. So to help me today, I'm joined by three leading experts in the field. So please welcome our guests today, Stephen Cool, Sam Ogonkolade and Stuart Miles. Now, shortly we'll be having a question and answer session with members of the audience, but first of all, let's set the scene and let's go to our first expert, who's going to explain his part in the business, who is Stephen Cool. Now, Stephen is a chartered structural integrity engineer and analyst with 16 years experience in structural integrity management and advanced analysis of both fixed and floating structures. At GL Noble Denton, Stephen manages the newly established Aberdeen SIM Group, which has a large number of SIM contracts for fixed and floating structures. The group covers a full range of SIM activities, from risk-based inspection assessments and defect management to finite element analysis for strength, fatigue and damage assessments. Now, Stephen, please could you summarise for us the process for structural reassessment of a floating unit, and can you describe simply how these structural assessments are performed?
Yes. The process for performing the structural analysis of a floating unit can be easily broken down into sort of a three-stage process. When you are awarded a contract to go and look at one of these floating units, the first bit of work you'll do is actually about data recovery. You will be recovering structural models, you'll be recovering reports, weight databases, all the pertinent information that you need in order to progress your analysis work. And having recovered all that information, the next thing you want to do is actually to review it. Now, when you're looking at, for example, the structural model, what you tend to find is that a lot of these units are circa 1970s and 1980s, and the analysis models you pick up may be of that vintage as well. And you'll all be aware that the computing power you have on your desktop today, or even at your home, is far in excess of anything that was available in the 1980s. And a lot of the models that we would typically recover have been cut down to size in order to limit the computing requirements. And what we can find is if the model hasn't been touched since, say, 1980, what we actually inherit is not particularly useful, and it might actually be just downright useless. We typically would look at shell modelling as the de facto standard for floating structures these days. But if you go back to the 1980s, it was beam modelling was the de facto standard. So what we inherit may actually not be as useful as the client perceives it to be. So having gotten all this information and having reviewed it, we get into the reassessment process. Now, the reassessment process itself is a staged process, if you like, and it's an iterative process as well. We typically will find ourselves working with a design contractor who is actually working on the design of the new blisters and new sponsons, whatever you're putting onto the unit. And that process is ongoing as we speak. It's ongoing as we're working. So we are constantly looking to keep up with what the design contractor is doing. So the first thing that we'll do is we start by developing our model. Now, the model that we're looking to develop, it may, as I've said before, be based on something quite old, so we're looking to maybe build a new model. And the key thing that when we're building the model, the key thing that we look to do is achieve an appropriate level of detail. Because although computing power has come on significantly since the 1980s, it's not come on as far as we would like, quite frankly. The software does not keep up. The software is far in advance of what the hardware is capable of doing. So we look at developing an appropriate level of coarseness in the model for the global model, but also developing the right level of detail where that detail is necessary. Typically, when we're building a model of a floating structure, we look to model the primary structure and the primary stiffeners as they actually are, without making too many assumptions. But we'd also look to model down to stiffener level as well, because these are stiffened panel structures. Now, we don't model every single stiffener, because that's just inefficient, and would lead to models that take days and weeks and months to run. So what we do is we look to just basically smear the stiffness of these stiffeners. Now, there are many approaches, but what we typically do is we model 1 in 5, and we use appropriate stiffness properties for the 1 in 5. When we're also working on this model, other features that we'd look to try and pick up are penetrations. Now, there's a graded scale of penetrations. You have your piping penetrations, for example, and we would ignore those because they're not important, unless they were near an area of local concern. Then you get up to sort of the manway size of penetration. Now, those penetrations are of some importance globally, but unless they're in the area of concern, they're not overly important. So we would tend to quite coarsely model these. Your typical manway has got curved corners, for example, to stop there being stress raises. We would just put a big square in. It keeps the modelling nice and simple. And the results, the poor results that would produce, we understand why they're poor. It's not a real problem, it's a mathematical problem. So having developed our model, the next stage that we go to is our hydrodynamic analysis, and that is one of the key parts of doing a floating structure, more so than in a fixed structure. The hydrodynamic analysis uses a combination of Morrison's and diffraction theory. Morrison's theory is for small volume elements and typically used for jacket structures, and has some application in floating structures, but not many. Floating structures tend to be large volume structures compared to the wavelength, so we use diffraction theory. Now, one of the things we have to do when we're doing an analysis like this is we develop what's called a paddle model, and that's basically a model of the wetted surface of the hull, and we use that for the analysis process. You can, if you wish, use your structural model, and that may well be the most efficient approach to it. But what we sometimes find is that these structural models can be very detailed, and they need to be very detailed. And they're basically too detailed for the computing power. So a lot of the time we will look to coarsening out that model and just developing a model of the wetted surface, the outer surface, and stripping out all the stiffeners. And that is just for the hydrodynamic analysis, it's not for the stiffness analysis. And what you will get out of this process is you will get a set of RAOs, which gives you the response of the vessel. You will get a set of pressures on the hull, which gives you the response of the water on the structure. And you will also get a mass for the vessel. And those three things together should all be in balance. And that's one of the key things that you're checking, is that these three things all balance each other out. And this is one of the things that we do where we understand that these are mathematical models. In order to get them close to real life, you've got to give that extra level of checking and that extra level of understanding about what you're doing. So having developed all this loading for the structure, we run into the analysis. Now, the analysis is actually the simplest part of the whole thing in some ways, because it's a standard analysis. It's a linear analysis process we go through. Now, when I say linear analysis, what I mean is that the materials will be assumed to be below yield and therefore give a linear response. And the displacements of the structure will be small in comparison to the overall size of the structure. So there's no significant yielding and there's no significant P delta effect either. And what the benefit of doing a linear analysis is it keeps it simple and it keeps the run times down to practical lengths of time. So you're running for a day rather than a week. If per chance we come across a particular problem in a structure and we want to investigate it further, we may pull out the more advanced techniques. We may look at non-linear assessments for areas that are exceeding yield. Large displacement analyses, to be honest, are rare, as most of these structures are moored and large displacements are not really an issue. Having run this linear analysis, we then get into the post-processing phase. And that's basically the reviewed results and setting the results in the context of an analysis code or a structural code. The type of checks you typically perform are your strength checks, yield checks, plate buckling checks, and one of our particular specialities is the fatigue type assessments as well. But I think that gives you an overview of the entire process and how we go about it.
Thank you. I've noted down a couple of questions and we'll come to those in a few minutes' time. But I'd like to hear from our next expert now. And our next expert on the Meet the Experts panel is Sam Ogunkolade. Now, Sam is a senior process engineer with 7 years' experience in oil and gas engineering, design and consultancy. At GL Noble Denton, Sam has been successfully involved in executing many process safety related projects. And Sam, you've got a presentation, so please come up and tell us more.
Thank you for the introduction. I'll be talking on process safety and how it's affected by changing needs, duty of equipment, and life of asset. To start with, what is process safety all about? Process safety is about preventing and controlling the potential release of hazardous material and energy, that is, preventing loss of containment. Process safety is not the same as occupational safety, which deals with preventing accidents to personnel working on facilities. Incidents that are process safety related occur infrequently, but their consequence could be very catastrophic. It could lead to significant loss of life, loss of reputation of the company, and many others. From concept selection through to design and eventual construction and operation of a facility, process safety is always put into consideration. But as the operation begins and with the passage of time, the asset might be required to be used for a purpose that is completely different from what was initially intended and designed for. This leads to a change. Change is any modification to the design and operation of the process. Some common example in the industry are tieback of a subsea pipeline from a new development to an existing floating production facility, addition of an extra unit like a dehydration unit or compression unit to an existing floating production facility, or relocation of an FPSO to another field to be used there. Following any type of change, no matter how minor, careful consideration should be given to ensure that no unintended hazard are introduced into the process as a result of the change. And also, all risks associated to the process are properly assessed. Impact on all existing safety critical elements should also be evaluated and requirements for new ones identified. Doing this will ensure process safety on any facility, no matter the change. As an example of an instance in which a change in process introduced unintended hazard into the process is Piper Alpha. I must emphasize here that I'm not talking about the accident in itself, but I'm talking about a change that happened many years before the accident. Piper Alpha began operation in 1976 as oil producing. About 4 years later, changes were made to the process on the platform to allow for gas production as well. However, some safety reasoning put into consideration during the initial design were violated while effecting the change. Initially, dangerous operations were distant from personnel area. After the change, gas compression was next to control unit. Also, in the initial design, process areas were separated by firewalls. These were never upgraded to blast walls after the change. These are hazards introduced into the process as a result of the change. No one could tell what difference it would have made if these hazards were properly identified and controlled when the change was made initially. How can GL Noble Denty help? GL Noble Denty provide a range of services that can help to ensure process safety in your facility at all times. These services include process safety verification studies. GL Noble Denty can help in the assessment of hazards and risk associated with your facility. We can do safety cases. We do relief and blowdown assessments. We can carry out lab extension studies, and we conduct hazard awareness courses and experimental testing. Thank you.
Thank you very much, Sam. We're going to take some questions in a moment, but first of all, let's talk to our final expert today, and that's Stuart Miles. Now, Stuart is an incorporated engineer as well as a fellow of the Institution of Gas Engineers and Managers. Stuart has been with GL Noble Denton and its predecessors for 31 years and was initially involved in both distribution and transmission operations. Over the last 15 years, Stuart has undertaken many integrity management projects for upstream oil and gas facilities, as well as on and offshore pipeline systems. So, Stuart, if you could come up and tell us a bit more, please.
Thank you, Paul. Okay, I'm going to do a short talk on the integrity management of aging FPSO assets using an integrity operating window management system, better known as an operating integrity. It's also easier to say. Okay, so what is an integrity operating window? First of all, you need to establish the limits for the critical process variables that can affect the integrity of your equipment. If the process operation deviates from these, then the predetermined amount of that deviation needs to be quantified. Areas that we need to consider will be temperature, hydrogen sulfide, CO2, the chloride content, the pH content of the fluids, the oxygen content, or the sand production. What we will have when we design the system, we'll have an optimum target for each of these variables. Primarily, most people concentrate on pressure. They will consider temperature. They will consider the others at the design phase, but once you move into the operation phase, then these are generally put on the back burner and not evaluated as effectively as they should be. So we set the targets. We have an operating range that we can work within, either in the high or the low range, that will not have any detrimental impact on the piping or the vessels that we're using. You start to move beyond these limits and you start to get failures with sustained operations at these levels. You move critically high or low beyond these limits and failure of your pipes and your vessels can come very quickly. We have had instances where operators have went through 36mm of carbon steel in less than a month by operating outside their design window in key areas, primarily in H2S and CO2. So what is an integrity operating window management system? We're looking at getting input in from plant data, so your historical data of your operation. You're getting live lab information coming from your labs on your vessels. You're getting your corrosion probes and coupon data from your providers, so you get to understand the deterioration within your pipes and your vessels. And you've got various analyzers and special instruments that you will measure the data that goes into your integrity operating window system. The output from that will then be inputs into your CMMS in terms of your job scheduling, and that may be SAP or Maximo, so you can plan your jobs. It will also feed into your anomaly management system so that any changes and deviations and excursions from your system go into your anomaly management system and you can proactively manage these and manage the degradation that you're predicting. And it would also fit into your risk-based inspection regime so that you can then update your risk-based inspection regimes depending on the deterioration that you're now predicting through the changes in your process conditions. So the potential benefits, you've got real-time monitoring of the key process variables and allows alerts to be triggered in a timely manner, not waiting till you have failure further down the line, or you wait 6 months and you've already lost half the wall thickness of your vessel or your pipes. That allows you then to make the corrective actions in a timely manner. You can refine your inspection plan and your corrosion monitoring activities based on the excursions. You've also got improved communications between production department, integrity departments and laboratory departments. Invariably within operators, these departments work in a silo and they do their own thing and communication is not there. One always tries to override the other, so we need to get these working together. And finally, you reduce the risk of premature failure. We're working with an ageing infrastructure, so it's important that we keep that operating as long as is reasonably practical, providing we manage it effectively. Okay, thank you.
Thank you very much, Stuart. We'll come to audience questions in a moment, but first of all, I've got a few questions I'd like to ask, and we'll go back to our first speaker. So we'll speak first of all to Stephen. Now, Stephen, I was wondering, how can the history of the vessel be taken into account when you're doing an assessment, and can that cause any problems at all?
The history of the vessel is important when you're dealing with one of these analyses, because what you have is you have a before and an after. And what you actually have is sometimes multiple befores and one after. And it's important that you incorporate that life cycle of the vessel into your assessment. It's important for two particular reasons. The first and most important from our perspective is from a fatigue analysis perspective, in that fatigue is a time-dependent mechanism and it's important to capture the response of the vessel at different phases in its lifetime as it's modified, which have different damage rates at different times. So it's important to capture each of those damage rates and how long it lasted for. The second, and sometimes less important because it's less frequent issue, is that as modifications are made to a structure, and the modifications might be made in a yard, but there are sometimes modifications made offshore as well, and the structure may be loaded in one particular way when the modifications are made, and that will affect the load paths in the structure. And it's important that you model that process all the way through so you get the correct representation of stresses rather than the stress representation based on the final model. Now, in order to properly capture all that, we want one single structural model. We don't want 5 models, each representing different parts of the thing's life, because as soon as you make one change, you find yourself having to make a change to 5 models. So we look to develop a single multi-purpose model, and we use what's called the super element technique, which allows us to effectively build the model up from blocks, building blocks. It not only does it allow us to build it up, but it also allows us to more efficiently process these models. Now, the problem with that is that we may have inherited a model, we may have developed one, but if we've inherited the model, it has refinement in particular areas for particular problems. Now, as we go on and we might add some new sponsons or some blisters or something like that, we generate new areas that previously weren't a problem. So what we find ourselves having to do is go and refine a lot of different areas in the model such that we can join it all together at the end, and at each stage in its life, look at the right piece with the right amount of detail. So that's a sort of description of the challenges that we face when we're looking at the history of the vessel.
But there must be some challenges in using historic design information.
Very much so. It's one of the major challenges, particularly working with floating structures. One of the major challenges we have is historic design information. Going back to what I was saying earlier, a lot of these vessels are particularly old and of a certain vintage, and it can be difficult in the first place just getting the design information. If your asset was developed in the 70s or 80s, the original design information just may not be there. And if it is there, sometimes we find it's poorly indexed. So we do find it eventually, but it does take a lot of time for us to find. And a particular problem we have is in the drawings of the vessel. Typically, these vessels were developed in shipyards, and again, going back to pre-AutoCAD days, they were all drawn on A0 or A1 shipyard type drawings, and they'll have been microfished at some point, and then they'll have been brought out of microfiche, and they'll have been scanned, and they'll be put in the computer. And when it arrives on your desk as an A3 PDF, the loss of fidelity in the details is astounding, quite frankly, sometimes. Another problem some people who are a bit newer to the industry may not realise is that when drawings were hand-drawn, the notes on them were frequently handwritten as well. It's possible to stencil the notes, but it's a very time-consuming process. And these notes and dimensions, section sizes are all hand-drawn, and you are sometimes dependent upon the quality of someone's handwriting. And you are left trying to decide whether that's a 6 or whether that's an 8. And sometimes common sense will tell you it's 6 metres and not 8 metres. Sometimes it's a section size and it is 6 inches, not 8 inches. But there are other times where you are left with a decision about what you do. And in those situations, you are looking at a pragmatic response to it. Is it a critical area? Are you going to spend a lot of time working out whether that's 6 inches or 8 inches, 6 millimetres or 8 millimetres? Does it make a difference to your analysis? Or are you happy to proceed with a slightly conservative assumption? Let's say it's 6 mil plate. It might be 8, but let's say it's 6 mil. Are you happy to proceed with that assumption? And that's where the skill lies in this, is judging what's an appropriate response to the given problem. One thing we can do to solve these problems is we can instruct a site survey. If the work's getting done in the yard or it's an accessible area when it's offshore, you can instruct a site survey to go and actually have a look at this. But the problem we tend to find with that is getting the right quality of information out of the survey. Typically, the person doing the survey is somebody at the yard, or it's a draftsman that you've sent out, and they don't understand the end product. They don't understand what you're trying to do with the information. So what happens is you get a lot of very good quality detail in areas you're not interested in, and the key areas where they make a real difference to your numerical model haven't been quite picked up on, and that's a process that you've got to be aware of when you send somebody out for a survey, and very clear instructions about the actual things that you're interested in. And moving on from the drawings, I think another thing that struck me has been a particular problem with historic design information is weight databases. It seems to be an industry-wide problem almost, that weight databases are maybe not given the attention and care that they deserve. And the information we receive can on a lot of occasions, not all occasions, but a lot of occasions, not be particularly useful to us. And there's a spectrum of problems with weight databases. And at one end, you have the weight database that's excellent quality up until 1982, and then hasn't been looked at for 20 odd years. And then you get the other one, which is it's excellent quality up to 1982, and then lip service has been paid for the last 20 years. And there's a lot of information in there, but it's so poorly referenced, so poorly indexed, and not given in the right format effectively, not a lot of sense put into how it's been presented, that it in itself is useless. And that's sometimes a bigger problem, because you are left with thousands and thousands of items of data with no real value to it, but you still have to plough through and try. You don't know there's no value to it until you've been through it, is the problem. So those are the two areas that I think that give us real problem with historic design information.
And the other thing is, of course, that I guess when you come to do an assessment, you can't just do it on its own. You're going to have to do it in parallel with other things that are going on at the same time. How much harder does that make your job?
It presents certain challenges, shall we say. I mean, you're never in this industry or in any engineering industry, you're never working entirely in isolation. It is always and always has been a team sport. But we find ourselves typically in a situation where we have a design contractor who's making the modifications to the structure, and they're working in one office, and then there's ourselves, as either the analysis or the sim contractor who's working in another office, and then there's the IVB, the Independent Verification Bureau, that's working in another office as well. And that presents a certain number of challenges, and the first one is the first aspect of this is that we're essentially working towards a moving target. When these projects kick off, there's an idea of what the final product's going to look like, but the detail hasn't been firmed out. And so your design contractor is constantly evolving, constantly changing what they're doing. And that, again, like I say, that presents us with this moving target. Now, from the analysis side of things, getting good quality FE models takes time. And sometimes the design contractor moves far faster than we can. And they will be, you know, maybe if it's a difficult project and there's a period of change, they will be firing off changes to us faster than we can deal with them. And because of that, we have to make judgments on the nature of these changes. The analysis, for example, can take, as I've said before, days and days to run. And if you're reaching, if you're that close to doing your analysis and the design contractor comes along and says, actually, we've changed our minds, we'd like to do this, this and this, you've got to look at it and say, well, is that a trivial change or is that an important change? You know, if you've said to me, I want to put a whole new bulkhead over there, I'm going to say, well, that's fine. But we're going to have to stop, we're going to have to revise our model and then run the analysis. If you say to me, I'm going to change the thickness of my T-stiffeners, I'm going to change the web thickness of those, I'll say, well, that's fine, we'll pick that up in the next revision, but we'll go and do the analysis. So it's about making judgments, and about the importance of a change and how it affects the model. And that's one of the big skills in doing analysis, not developing fancy mathematical models, is understanding the engineering behind what you're doing. So we get into this process of doing these cycles. But one thing you can get too focused on is always making changes to the model as the contractor makes these changes. Sometimes, because the model takes a long time to run, and you never have a true knowledge. These are complex structures, and you never have a true knowledge of them until you've got the first pass done. So sometimes you'll take the view that, okay, that's a major change, but I'm still going to run my analysis tonight because at least I get some information out of it, and that will inform my discussions about how important this latest bit of knowledge you presented to us. So that'll inform my decision about that. And I think the third problem that we see is it's about differing goals within the process. I mean, there are typically three goals within any engineering project. You want good quality, technical robustness, you want to be on time, and you want to be on budget. And those three goals, it's brilliant if you can get them all to come together at the same time, but that is not always the case. And you find that different parties have ranked those goals differently. Your design contractor, coming from a big project environment, is very focused on schedules, times, budgets, things like that. And that's important because if you're cutting steel in a yard, it's very important to be focused on the schedule aspect of it. Your IVB has no such concerns, and their focus is purely on the technical response, the technical robustness of the response to the project. And as the analyst, you tend to get trapped in the middle of these two parties. And again, it's about developing a pragmatic approach to any given problem and understanding that on some occasions a simple WL²/8 conservative approach to the problem is more than adequate. So you can still give technically robust but conservative response and keep your time and your budget all nice. But there are times when that just is not appropriate. There are times when you can't do that simple conservative approach. There are complex problems. And in these situations, you've got to be able to say, we need to push the technical robustness side of things a bit more. It may run the budget or it may run the schedule a bit longer, but there's a good, valid technical reason for doing that. And I think what's important to demonstrate is that you understand both sides of that problem. Because I think if you demonstrate to both parties involved, the IVB and the design contractor, that you understand on any given day a conservative approach is best or a high-tech approach is best. They start to trust your judgment on when to swing between the two of them. So I think that sort of describes the particular challenges that we have when we're dealing with these different parties.
Lovely, thank you very much. We'll come back to Stephen in a moment if any members of the audience have a question for him. But Sam, I want to move on to you, and I was very interested in all you said about process safety. Is there sufficient emphasis, do you think, in the industry on process safety?
There should be, but most companies place much emphasis on personal safety more than process safety. And really, there should be much focus on process safety because this deals with preventing major hazards like gas explosion and fire. This accident could result in significant loss of lives, environmental damage, damage to the asset, lost revenue, and lost reputation for the company. And again, passage of time without having a major accident is not in itself an evidence that things are well with the process. Rather, this could contribute to a dangerous sense of complacency that will lead to hazards and deviations from safe operating mode becoming accepted, which will ultimately result in accidents. So therefore, for these reasons, there should be continuous focus on process safety until the process is decommissioned.
And in your presentation, you talked about how there was a change and then not necessarily the correct process safety maintenance afterwards. How do you maintain process safety after a change?
Most organizations have management of change procedure that must be complied with before a change is effected. And usually, these procedures will require that the hazard and risk associated with the process in relation to the change be reassessed. And once this is done, steps should be taken to reduce the new risk associated with the process based on the change to as low as practical. Actions and steps that have to be taken to achieve this will depend on the change itself. But it usually involves evaluating the impact the change will have on safety critical elements in the process, and then assessing the requirements for new critical safety elements that has to be added to the process. For instance, if there's a tieback of a subsea pipeline from a new development to an existing floating production facility, this may require the installation of EIPs depending on the pressures involved, the source pressure and the design pressure of the existing facility.
Okay, and we have also touched in the discussion so far on ageing assets. Is there anything special you need to do when it comes to process safety with older bits of kit?
Yes. As the asset ages, the associated hazards and risk changes. These changes must be captured through appropriate inspection regime, maybe through risk-based inspection, and subsequently, the new risk associated with the facility now needs to be managed. Because basically what happened when asset ages is the layers of protections that has been put in place when it was new, they are basically being taken off one by one until the last one is taken off, and it's going to lead to a major accident. GL Nubudenti offer a range of services that can help in managing aging assets such that process safety is going to be maintained. These services include review of safety cases, risk-based inspection studies, revised fire and explosion assessments, process safety verification studies, and many more.
Okay, thank you. Stuart, I'd like to pick up on what you were talking about with IOWs, and I made a note of this. How can an integrity operating window management system actually improve the asset lifecycle integrity management practices you were talking about?
It allows you to be proactive in terms of what mitigation you put in place to manage the threats to your system. And it shouldn't be seen in isolation as a standalone integrity management system. It should form part of your overall asset management system that sits alongside your pipeline integrity management system, your asset integrity management system, your structural integrity management system, your corrosion management system. They're all taking similar inputs. You're conditioning that data to give you the information that you need to then make proactive decisions on how best to manage your facility.
Okay, and how does an IOW management system link in with an RBI system?
You need to understand the threats to what's causing the degradation of your pipes and your vessels in your facility. So once you understand the threats, then you need to mitigate these threats and manage these threats accordingly. So by understanding the changes to what's happening with your production chemistry gives you then the information that you require to make a proactive decision to say, we believe that the corrosion rate in this pipe is going to be higher than we'd originally planned. Therefore, we need to inspect it more frequently to understand that it's actually deteriorating as we envisage it deteriorating, or we may introduce more chemicals into the production stream to mitigate that change in the process chemistry.
Makes sense. Okay, I think we've had enough of my questions. We should now turn and hear from the audience. So we've got time for probably half a dozen questions, I should imagine. So does anyone have a question that they'd like to ask our panel, please? Gentleman at the back in the orange-coloured tie, please. If we could get a microphone to him.
Sam, my question's to you. In your presentation, you put a slide up which showed a range of services provided by GL Noble Denton. And the first one was, what is process safety verification study? I would like to know exactly what it is, please.
Thank you for that. This is independent desktop verification of process design that we carry out. What we do this for is to ensure that all hazards relating to the process has actually been identified and properly controlled. This involves we verifying that the design is actually done to appropriate philosophies and standards. It involves we checking that proper safeguarding and proper and adequate safeguarding have been put in place for the process. We also review and verify the relief and blowdown assessments to ensure that all credible relief scenarios has been considered and that the safety valves are actually sized for the worst case scenarios, and that blowdown of the system has been designed such that the system will be safely depressurized fully. We also look at other things like the HPLP interfaces, if they have been properly done. We look through the HAZOP and the closeout of each actions, and we look at the layer of protection analysis that is adequately done as well. We conduct this for new designs and existing facilities. For new design, we do carry this out towards the end of feed and detailed design. For existing facilities, it could be done whenever any modification has been done to the facility.
Thank you. Next question, please. Gentleman here in the stripy blue tie, please.
My question's for Stuart. Could you tell me how do we determine the integrity operating window limits for an asset, please?
Yeah. For every material, it will have a limit of what production chemistry it will be able to convey safely. So, for example, the amount of CO2 in your process stream, through various databases, you can determine what the corrosion rate will be depending on the level of CO2 in the system. What you can also then do is determine what limit you can actually run the system at for certain periods of time that will still allow the pipes and the vessels to remain in a safe condition and not deteriorate quicker than planned. using the same databases, if you increase the limits, you can then calculate what corrosion rate you will then plan to have should the percentage go up, 50% or whatever. So you can then determine when you need to intervene, and each case will be completely separate depending on the exact production chemistry and depending on what materials you've actually used. If you go in and use some of the stainless steel instead of carbon steel, then you will get significant benefits in the range that you can operate within, but then you have a cost implication of installing that. Or you could move into the Inconels, but again, it's a cost-benefit ratio that you need to consider of how much monitoring you want to put in place against how much capital costs you've got. With the ageing fleet, and if you move an FPSO onto a new station, you will be limited with the materials that are already in there. So therefore, you may be locked into a predetermined category of material to work with. Therefore, you then need to determine what percentages you're allowed to work within using primarily the corrosion engineers' experience and the tools that are available to them.
Great. Next question, please. The lady there with the necklace, please.
I'd like to ask Stephen, how do you follow through from reassessment to operations?
Yes, I think with that question, you could boil it down to a one-word answer, which is knowledge. A two-word answer would be knowledge retention, which would possibly be better. But let me expand on that a little bit. When you're in a design project, you have a self-contained team of engineers who are working on whatever the modification is, and those engineers, their focus is on delivering the project, and their involvement generally ends when the project's delivered. And what you've then got the other side is a group of operations guys who are interested in not just today, not just tomorrow, but 5 years and 10 years down the line. And it's making the link between those two groups of people that's the key thing. And the issue is about knowledge. 99% of the knowledge that you need is transferred through design reports, drawings, weight databases, structural models. That's all transferred. That's your standard deliverables from one of these projects. But there's that final 1%, and a lot of the time it's not the what was done, but the why it was done. Sometimes the fine detail of the why something was done is lost in the mist. And it might not be important during the design project. It might not be important on day one of operations or your revised operations. But 5 years down the line, when you're coming to add more to your structure, you want to add another part to the structure, and you want to look at the whys and wherefores of why particular things were done, why sequences were followed. It's then that key knowledge is lost, and that knowledge has a value greater than money, because you can sometimes never recover that knowledge. It's like historic drawings. When they're lost, Now, sometimes the sim contractor will be involved in the entire process, and your sim contractor can provide that continuity through the entire process. But in order for them to do that, you've got to almost take them just out of the sim box and let them see the wider project. If you keep your sim contractor involved in not just the decisions that influence him today, but the entire project, they can help retain knowledge, because your sim contractor tends to be a long-term relationship. There are situations, however, where your sim contractor, for whatever reason, is not involved in that process. The work's getting done by somebody else. And I think it's still important to try and retain that knowledge. And how you do that is through engaging your sim contractor very early on in the design process and keeping them involved all the way through, and they will help you retain that knowledge. And if I could take one thing from the entire presentation that I've given today, I think that would be it. I think it would be about early engagement with sim and the value that the knowledge retention will give you, not just now, but 5 years and 10 years down the line.
Okay, got time for two more questions, I think, please. Gentleman there in the stripy tie, thank you.
I'd like to just ask Sam, what are the benefits of the process safety verification studies?
Thank you for that question. I will use an example of a project we completed recently. we verified the process safety aspect of a detailed design of a large gas facility recently, and part of the verification involved assessing the proposed automatic stagger blowdown for the facility. What the verification study revealed is the timing being proposed to be used for the stagger blowdown will result in design capacity of the flare system being exceeded. So this was corrected after our study, and basically averted a potentially hazardous situation.
Okay. One more question, please. Gentleman just in the front row here, please.
Stuart, I've got a question for you. What actions can we undertake if there are any excursions to the integrity operating window limits?
There's two key areas or two key actions that we can take. We could either evaluate and review the inhibition systems that we've got in place to mitigate the change in the production chemistry. So we may put more corrosion inhibitors in, etc. Or we can amend our inspection regime. So we can do more monitoring of the inspection, gather more data to validate if the actual deterioration is as planned. Because ultimately that's the whole point of the inspection, is to validate what you've planned or envisaged will happen in terms of deterioration. So more inspection, more detailed inspection at critical areas to see if what you've planned will happen is actually happening in practice.
Okay. Thank you very much for the questions, audience. Gentlemen, before I let you go, just want to pick up on a couple of points. First of all, it's cropped up a couple of times while you've been talking, which is the ageing asset issue. Some of the assets that we're actually using out at the moment are actually way beyond the age that they were expected to last. How much of an issue is that for us?
It can be an issue if you don't have the data and the information to back up the continued safe operation. So it's important that you have that information available, that you know the condition of your asset, that you're not running blind. And in my view, if you've got that information available and you're using that correctly through your management systems, then I believe they are still safe to operate.
Okay, so Sam, there's no safety issue provided you follow all the checks and balances.
Yes, basically it's not really about how old the asset is. It's much about what you know about the conditions in which they are. Are they in the condition that they can be operated safely? If not, then you have to do the appropriate thing to bring them up to date.
Okay. I think I'd just like to add to what my two colleagues have spoken about, because I think there's a theme developing here, which is knowledge. It's about understanding the condition of your asset. I think an asset that's beyond its design life is not necessarily an issue if it's been well maintained. And when I say well maintained, I don't just mean from a corrosion management point of view. I don't just mean is it well painted, but are your systems back on shore well maintained? Do you have good records? Can you trend corrosion, for example? So I think it's about understanding the condition of your asset. And in order to understand the condition of your asset, you've got to have that knowledge. And so knowledge, again, like I say, it's worth more than money.
And talking of knowledge, when it comes to the fact that here we are in Aberdeen and the equipment that we're using here is used to being battered in the North Sea, but around the world you will have different requirements. How much different knowledge do you need depending on where you are in the world using perhaps very similar kit?
I think to take a point there and say very similar kit, I think the North Sea experience of structural integrity is very different to, say, the Gulf of Mexico experience of structural integrity. In the North Sea, each unit, each platform is a bespoke item, and it's managed individually on its own. And that gives us one set of challenges or one set of problems. I think if you go elsewhere in the world, Gulf of Mexico, for example, there are a far more assets, but they tend to be there are less manned assets, for example. and they don't manage their assets on an individual basis. They manage them more on a fleet basis. And I think, whilst the structures may be similar, I think the approach on a sort of fleet basis is very different, where rather than looking at one asset and its unique and particular problems, you're trying to trend problems across a number of assets and look for solutions that are more appropriate to be applied on a large scale. But I think there's lessons to be learned in the North Sea from the Gulf of Mexico experience, and indeed the Arabian Gulf as well. Particularly when we get into the wind turbine market, because the wind turbines, they tend to be 200, 300 very similar jackets, and it will at that point be a fleet management problem rather than a single asset management problem. So I think there's lessons to be learned there, and I think we're quite lucky and we're well placed, having offices worldwide, that in Aberdeen we work on the North Sea approach, but in Kuala Lumpur, for example, we work on a more sort of Gulf of Mexico style approach.
From a pressure equipment point of view, the concept is the same. You need to understand the threats, mitigate these threats and manage these threats accordingly. The changes that you do have is in certain areas of the world the products may be more corrosive, and also in different parts of the world you will have different legislative requirements. In the UK we have a goal setting requirement that works well. Whereas you go to certain areas in the Middle East and it's very prescriptive that you must do certain things. But ultimately it's about understanding the threats and mitigating these threats so you maintain a safe asset.
Well, thank you very much, gentlemen. I'm afraid we're out of time now, but I'd very much like to thank Stephen, Sam and Stuart for their time. Don't forget, we do have another Meet the Experts session, which is about FPSOs and understanding the technical, environmental and regulatory aspects of those. But for now, that's all we have time for. I'd like to thank our guests once again from GL Noble Denton, and I'd like to thank our audience, and join us again soon. Goodbye.